Hi everyone, welcome to today's presentation of Wisent Robust downstream communication and storage for computational RFID. So now we'll talk about the CRFIDs overview of the paper. So the CRFIDs represent a remarkable innovation facilitating sensing and computing by harnessing energy from ambient radio waves. However, despite the considerable attention directed towards optimizing upstream communication from CRFIDs to the reader, the pathway from the reader to CRFID has regrettably been largely disregarded in prior research endeavors. The Wisent protocol, which we proudly present today, aims to rectify this oversight by offering a robust solution for downstream communication to CRFIDs. Before delving into the intricacies of the Wisent, it is imperative to understand the rationale behind its development and implication of its implementation. The primary motivation for Wisent stems from recognition of indispensable role that bidirectional communication plays in maximizing the utility of CRFID technology. While upstream communication enables data collection and analysis, downstream communication facilitates interaction and control, allowing the reader to transmit instructions or update directly to the CRFID. Vision distinguishes itself through its emphasis on reliability, efficiency, and adaptability. By integrating advanced error correction mechanisms, Vision ensures resilient data transmission, even in adverse conditions characterized by noise or interference. Moreover, Vision optimizes energy utilization, thereby extending the operational lifespan of CRFIDs and enhancing their sustainability. Furthermore, Vision offers scalability, versatility, enabling seamless integration into diverse deployment scenarios. Whether in industrial facilities, agriculture fields, or environmental monitoring systems, Vision can accommodate varying requirements and environments, providing a standardized yet adaptable solution for downstream communication to CRFIDs. The practical implementation of Vision are far-reaching and profound. In industrial settings, the Vision facilitates real-time inventory management, logistics optimization by enabling direct communication with CRFID-enabled inventory items. In environmental monitoring applications, Vision empowers researchers to gather and analyze data on biodiversity, climate patterns, and environmental changes. As we contemplate the future implications of Wisent, it becomes evident that its significance extends beyond the confines of current applications. From smart cities to healthcare systems, the integration of Wisent-enabled CRFIDs holds the potential to revolutionize various sectors. And by addressing the critical aspect of downstream communication, Wisent not only fills a significant gap in existing research but also paves the way for new possibilities and innovations. With Wisent leading the charge, the future of wireless function and computing appears exceedingly promising. So this was a brief overview of the technology and the paper and how it can be used in the whole world and what it can do. We'll now see the challenges that were faced by the authors of this paper. Um, Moving next, we'll see the challenges. So there are two main challenges in enabling CRFID downstream communication. First, the existing EPC-C1G2 RFID communication protocol, and this does not have built-in support for fast transfers of large data from the reader to the tag. And second, the CRFIDs experience frequent power interruptions due to transient power availability, which can lead to data loss and state loss. And this transient power issue is illustrated in the figure. So, this paper makes three key contributions. First, it leverages the functionality of the EPC C1G2 protocol to implement and evaluate multi-word downstream data transfer, showing a threefold improvement in downstream throughput. Second, it designs, implements, and evaluates Wisent, a downstream-oriented protocol for CRFIDs that can adapt the message size based on channel conditions to minimize data transfer errors. Third, it implements and demonstrates the world's first wirelessly reprogrammable or software-defined CRFID, enabling true reprogrammable radio sticks. So in a typical CRFID system, as shown in the figure A, the host machine communicates with the RFID reader using the low-level reader protocol or LLRP. So the reader then communicates with the RFID tag using EPC C1G2 protocol as shown in the figure B. So the authors first evaluated the performance of the block write command, which is a key for enabling faster downstream transfer rates. They tested word count sizes ranging from 1 word up to 32 words. The results showed that using block write can provide up to threefold speed up in throughput compared to single word write command. However, errors increased significantly at longer distances between the reader and the CRFID. The first version, called Wisent Basic Design, uses the write command, which is limited to just one word payloads. It employs a header byte to identify whether the payload contains address, information, or data. For verification in Wisent Basic, a copy of each message is kept by the host to compare with CRFID's backscattered EPC. An example message transfer is shown in the figure. Now, to overcome the one-word payload limit, the authors designed an extended version called Wisent EX that uses the block-write command for larger payload sizes. It also introduces an adaptive throttling mechanism to adjust the payload size based on channel conditions. So instead of copying messages, Wisent X uses a checksum for verification. So in Wisent X, the authors propose a new message format shown in the figure to accommodate larger payload using block write. Now the throttling mechanism in Wisent EX works as follows. It defines a set T that contains possible payload chunks. So the payload size SP is increased after M threshold consecutive successful messages. However, SP is decreased using the constants TDE or TDL after a timeout, which could be caused by various reasons like reader losing sight of the CRFID. So for implementation, the authors used an x86 PC running Ubuntu 14.04 as the host along with the LLRP library. So the RFID reader was an impinged Speedway to R420. As the CRFID platform, they used WISP-5, which features 64 KB of FRAM memory. So the CRFID system setup was which was used for recent experiment is shown in the figure on the slide. Now the authors proposed model functions ftx and gnrx to describe the relations between the word count size and throughput and efficiency for block write. The model showed a mean R/2 value greater than 0.97, indicating a very good fit to the measured data. Now, several performance metrics were defined to evaluate Wisent, including messages per second, success operations per message, total operations per message, throughput resend rate, and efficiency. In their experiments, the authors observed up to 3.8 messages per second using the impinged R420 reader. They found that the setting operation count value or OCV to 15 optimized the window before deleting the access spec. Overall, Wisent achieved throughput up to 16 times faster than one word baseline. The authors proposed a condition for selecting the values of throttling parameters TU, TD, and TTL. They selected TU is equal to 1, TD as 2, and TDL as minus 3, and Rmax as 3, and M threshold as 10 for the implementation. So as the final evaluation, the authors demonstrate the ability to wirelessly program the WISP by using the Wisent X with selected parameter values in section VB3. For this, they created a bootloader that is manually programmed to the WISP and is not overwritten after the wireless programming. To initiate the wireless programming, the host sends a transfer initialization message as write command to enter programming mode. This command is recognized by the CRFID so that the messages are handled correctly until the programming session is finished. When all data of the application is transferred, the CRC16 checksum over the whole application is sent to validate the firmware. If the checksum matches the calculated one on CRFID, the programming session was successful and the bootloader will start the application again. So as the experiments, they have adapted a measurement scenario to mimic movement of CRFID and its effect on channel quality using an in-house developed automation for repeated intermobility. So for this, the wisp is attached to nylon wires, which are then wound up, released by stepper motors controlled by an Arduino with the speed of approximately 0.1 meter per second to move the wisp and change its distance to antenna between 20 and 90 centimeter, which I'll be explaining the results in the next slide as well. This distance is the distance between the optimal. It is between the optimal distance and a distance where channel is unreliable in the repeated manner. Result justifies the use of throttling mechanism as proven in section 4D3 of the paper. So in comparison with the case of a set SP is equal to 4, the throttling mechanism cuts the transfer time of base firmware down by approximately 100 seconds and even reduces the recent rate with almost 3 times while finishing all transfer attempts. Now, for result completeness and comparison to typical state-of-art WSN devices concerning the energy consumption used in downstream communication, they have used a monsoon power monitor to measure the energy consumption of a T-mode Sky node, storing 5387 bytes of data received from another node. So to represent the recent text and messages in the experiment that the authors have done, the data was sent in chunks of 32 bytes with XMAC protocol present in Contiki OS, and the measured energy consumption of the T-mode Sky is 256.35 millijoules, while the WISP consumed a total of 81.7 millijoules. And this proves that despite Wisent not being designed with energy efficient in mind, CRFID downstream transfer is at least 3 times more energy efficient than corresponding WSN downstream. So as an ultimate experiment, they demonstrate the ability to wirelessly program a tissue-implanted CRFID to emulate such a scenario. They placed a cling film warped wisp between 5 and 6 layers of meat which was bacon, and on top of the and at the top and the bottom of the wisp respectively placed an antenna separated by a 6 centimeter paper box. So this experiment followed similar ex vivo experiments simulating implantable sensor scenarios. They were able to successfully program the wisp with complete RFID stack between 63.55 seconds despite the attenuation of the backscatter signals from the meat. So for the reprogramming experiments, the authors adapted a moving setup to vary the distance between the CRFID and the reader's antenna from 20 centimeter to 90 centimeter. The results showed that the throttling mechanism reduced the transfer time by approximately 100 seconds compared to a fixed payload size. They were able to successfully reprogram the CRFID even when it was embedded in layers of meat. The authors adapted a moving setup shown in figure A to vary the CRFID distance. They also demonstrated reprogramming CRFID embedded ex vivo layers of meat as shown in figure B. So in terms of energy consumption, the WISP consumed 81.7 microjoules for transferring 5387 bytes of data using Wisent. This was found to be 3 times more energy efficient compared to a typical wireless sensor network device like a T-mode. So now we will look at the limitations and future work of this paper. So while Wisent forms a solid baseline for experiments and application involving computational RFID communication, several additional features are necessary to enhance its capabilities and address real-world deployment scenarios. The authors have identified the following key areas for further development. transfer to multiple tags simultaneously. Although Wisent was designed for efficient data transfer to a single CRFID tag, extending its functionality to support simultaneous transfers to multiple tags is crucial for scalability and broad applicability. This extension would even involve careful scheduling and allocation of resources, such as time slots and communication channels, to ensure reliable and efficient data delivery to multiple computational RFIDs concurrently. Then we can talk about the security mechanisms to enable the deployment of reprogrammable CRFIDs. In practical application, robust security measures are essential to protect the data transfer process and prevent unauthorized access or message spoofing. Wisent in its current form lacks mechanisms to ensure data integrity and authentication, which could lead to vulnerabilities if not addressed. The authors emphasize that incorporating security features is the most urgent requirement missing in Wisent, as it is crucial for enabling secure and trustworthy wireless programming of CRFIDs. Then we can talk about the resumption of interrupted transfers. In real world scenarios, data transfers may be interrupted due to various factors such as power outages, inference, or communication failures. Incorporating the ability to resume an interrupted transfer from the point of interruption rather than restarting from beginning could significantly improve efficiency and reduce the overall transfer time and energy consumption. Then data compression mechanisms to further optimize the data transfer process and potentially increase the throughput. The authors suggest considering the addition of data compression mechanisms. However, this feature would introduce a trade-off between the performance gains and computational power required by the CRFID to perform decompression operations. Careful evaluation and analysis would be necessary to determine the optimal balance between compression efficiency and resource constraints on the computational RFID devices. So the authors argue that addressing these additional features is crucial for enhancing the practicality, scalability, and security of CRFID communication system based on Wisent protocol. By incorporating these enhancements, Wisent could become a more comprehensive and robust solution, enabling a wider range of applications that leverage the capabilities of wirelessly reprogrammable computational RFIDs in various domains, such as wireless sensor networks, Internet of Things, IoT deployments, and other embedded systems that require efficient and secure data transfer and remote programmability. So now we'll move forward to the conclusion of this paper. So coming to the conclusion, in this research paper, the authors have designed and implemented an innovative protocol called Wisent Wireless Sensor Enabled Non-Volatile Transfer that enables efficient and robust bulk data transfer for the host system to a computational RFID device. So CRFIDs are RFID tags with additional computational capabilities, making them suitable for various applications beyond traditional RFID use cases. The Wisent protocol addresses several challenges in transferring large amounts of data to CRFIDs, including the need for fast data transfer rates, robustness against power interruptions, and efficient utilization of the limited communication bandwidth available in RFID systems. One of the key features of Wisent is its ability to store and verify data on CRFID. Despite power interruptions during the transfer process, this is achieved through the use of non-volatile ferroelectric random access memory (FRAM), which retains its data even in the absence of power. Additionally, Wisent incorporates a simple error verification mechanism to ensure data integrity. To improve the throughput of data transfer, Wisent introduces the concept of large frame sizes for data transmission from the RFID reader to computational RFID. This is made possible by leveraging the capabilities of EPC Class 1 Generation to C1G2 RFID communication protocol, which supports variable frame sizes. By dynamically adapting the frame size based on channel conditions, Wisent can achieve up to threefold improvement in throughput throughput compared to the standard single word message size specified in EPC C1G2 standard. Furthermore, the implementation of Wisent protocol has enabled the world's first wirelessly reprogrammable software-defined computational RFID. This groundbreaking achievement allows the CRFID's software to be updated or reprogrammed wirelessly, enabling flexible and dynamic functionality without the need for physical access or hardware modifications. The authors have thoroughly evaluated the Wisent protocol through experimental verification, demonstrating its effectiveness in enabling fast, robust, and reliable bulk data transfer to CRFIDs. This research work it paves the way for more and more advanced and versatile CRFID applications, opening up new possibilities in areas such as wireless sensor networks, Internet of Things devices, and other embedded systems that require efficient data transfer and remote reprogrammability. So, thank you.